So today we're going to change directions, talk about something completely different from distributions. Spent the first two lectures discussing. So before we begin, I'd just like to comment that the lecture notes are updated. I posted the wrong file yesterday evening on my way to pick up my son from daycare and fixed that this morning. So if you see, you printed out the handwritten notes. Those were from a previous version of the course. They'll sort of correspond to what we're doing today, but not precisely. The LaTeX lecture notes are up now. So we're going to spend approximately the next two lectures discussing asymptotics and asymptotic series. And our main example of, or main method for constructing asymptotic series is going to be the saddle point approximation, which we'll get to at the end of today or beginning of tomorrow's lecture. And so what asymptotic series are, they're in general, they don't converge like convergent series, Taylor series that you're familiar with. They're not, series can be both asymptotic and convergent or one or the other. So they're not, it's not a generalization, but rather another type of series that we can construct. And in physics, when we're using a saddle point approximation, which is a key approximation that we'll use all the time when we're studying the path, using the path integral quantization of quantum mechanics or the functional integral quantization of quantum field theory. It's a technique we'll use over and over again. And in general, when we're using that approximation, what we get are asymptotic series that are not convergent. And so the main goal of these next few lectures is to understand, one, how to use the saddle point approximation, and two, how to make sense of the result, because the result is often not a convergent series. And so let me just give you a brief outline of where we're going over the next two lectures. So first, I'll very briefly discuss the gamma function for two reasons. One is that it will provide a nice example of some of the techniques that we're going to use. And the second example is that it has a different but important application in quantum field theory, namely to a regularization technique, a technique for making divergent integrals finite, called dimensional regularization, that we'll examine more in tutorial this afternoon, and we'll discuss regularization and related topics more in the final lecture. And so we'll begin with a brief discussion of that. Then we'll discuss what is an asymptotic series. So we'll go through some definitions. And then we will begin our task of trying to figure out how to construct them. There's many ways to construct asymptotic series. There's one method that's far more important for physics, so that's basically the only method we're going to talk about. And so we'll discuss first Stirling's approximation. So that's a simple version of the saddle point approximation applied to the gamma function. And then we'll discuss the general saddle point approximation. And while we do that, we'll discuss some of the subtleties that go into this. So in particular, we'll discuss Stokes phenomena, which is one interesting thing that can happen to the saddle point approximation. You can basically have different asymptotic series that work in different parts of the complex plane. So that we'll probably end somewhere around here today, and tomorrow we'll finish up with this. And so that's where we're going over roughly the next 2 lectures. Okay, so before we get into our main topic, which is asymptotics, I just want to briefly say a few things about gamma function. Again, our motivation is, as an example, or the saddle point approximation, and dimensional regularization. So in tutorial. Okay. So the gamma function is a generalization of the factorial function. Factorials are just defined for the integers. Gamma function is defined over the whole complex plane. And what we'll care about for this second application is the location of the poles. And we can see that just after just a short discussion of what this function is. So that's going to be our main goal, is to figure out where the poles of this function are and what its residues are. And along the way, we'll see how it's related to the factorial function. So the gamma function is defined by this integral. And so this integral converges. So it goes to 0 rather quickly as t goes to infinity because of this exponential factor. But if we want to figure out for what z this converges, we need to look at this t to the z minus 1 factor. So if z has a particular z has a negative real part, then this won't be integrable near t equals 0. But as long as the real part of z positive, then even if the integrand blows up, it'll be integrable near t equals 0, and this integral will make sense and converge. So this is a definition of the gamma function on half of the complex plane. We're going to need to do better than that. For this application, we're going to need to define it on the whole complex plane. And we can do that by defining the functional equation. So one of the key properties of the gamma function is that it's a generalization of the factorial. And one of the key properties of the factorial function is that n factorial is n minus 1 factorial. So this is what we call a functional equation. It relates the value of the function at one point to the value of the function at another point. And since this is a generalization of the factorial, it should have the same property. We can see that in just a few lines. So to see that, note that the derivative of t to the z, e to the minus t, is z t to the z minus 1, e to the minus t, minus t to the z, e to the minus t. And each of these factors looks like the integrand of the gamma. So if we integrate this equation, we can relate gamma at with different arguments. So this up to some factor is the integrand of gamma of z. This is shifted. So this will give us the relation we want. If we just integrate this from 0 to infinity, and so this first, the left-hand side of this equation just vanishes at both of the boundaries. At t equals 0, this t to the z factor vanishes. At infinity, this t to the e to the minus t vanishes. So over here we've got a 0. And this is just z times gamma of z minus gamma of z plus 1. So that's just the kind of relation we were looking for. We've got gamma of z plus 1 is z gamma of z. And together with the fact that gamma of 1 is 1. You can see that just from the definition. If we take z equals 1, this factor goes away. Integrate e to the minus t from 0 to infinity gives us 1. That tells us that allows us to make the identification that gamma of n plus 1 is n factorial. So it's shifted. Rather unfortunate fact. But historically, based on history, we're stuck with that. Okay. So that's the sense in which gamma is a generalization of the factorial. It agrees with the factorial when both are defined. And so now that we have this functional relation, we can use it to figure out both the poles and the residues of the gamma function, which is the main fact we'll need. We'll need two things. We'll need this original definition, and as well as the location of the poles and residues. Okay, so we need to extend gamma to the whole complex plane. So we've got a definition for half of the complex plane. We know how to relate the value of gamma of z plus 1 to the value of gamma of z. And by putting these two things together, we can define gamma on the whole complex plane. So we've got a definition that works over here. If we're interested in a point over here, well, we can use the functional relation to relate it to a point that's 1 away and repeat the process. So we can use the functional equation. Repeatedly to define the value of gamma at this point in terms of the value of gamma here. And in equations, what that says, what this picture is trying to say is that gamma of z can be defined to be gamma of z plus n over z plus 1 up to z plus n minus 1. So this, we can make sense of gamma of z for any z. If the real part of z plus n is positive, then we can define the numerator in terms of the original integral, and everything else on the right-hand side makes sense. So the integral together with the functional relation allows us to define gamma on the entire complex plane. And what we care about are the location and residues of the poles of the gamma function. It's really important in tutorial this afternoon. And so, well, from this relation, together with the fact, which I'm not going to show, that gamma has no zeros, suggests that there are poles at the negative integers and 0. So gamma has no zeros. Poles at z equals minus n for n greater than or equal to 0 from this equation. And the last thing I want to say about the gamma function is that the last thing I want to do is to figure out what the residues are. We'll need that this afternoon. And we can do that if we know where the poles are, just by setting z equal minus n minus 1 plus epsilon. And in that case, just using this equation up here, get gamma of z is, so this first factor will just give us an epsilon. The next one will give us an epsilon minus 1, and so on, all the way down to epsilon minus n minus plus 1. Plugging this in here. And for epsilon small, this is approximately gamma of 1 is 1. N minus 1 or n plus 1 of these factors will be negative on basically everything except for this first one. So we get a minus 1 to the n plus 1. And these factors just become n minus 1 times n minus 2 down to 1. So n minus 1 factorial. And there's an epsilon left over. And so this is telling us that the poles we identified are all simple poles, and they have residue minus 1 to the n plus 1 over n minus 1 factorial. Oh, sorry, we shifted things, so we need to unshift things. So we get minus 1 to the n over n factorial. we'll use this result in tutorial this afternoon. And yeah, it can be shown that there are no other poles as well. So these are the only poles. Any questions on the gamma function? Okay. Sure if I want to use that board. If it's visible then. Okay, so now we're going to move on to our main topic of interest, asymptotics. And so this topic has a broad range of applicability. So in general, these ideas are relevant whenever we want to understand the behavior of some object or system when a parameter is large or small. Sometimes you can use convergence series to study a system when a parameter is large or small, but not always, or not always easily. And as I alluded to before, one of our main techniques in the path integral and functional integral formulations is the saddle point approximation, which will give us an asymptotic series. So we want to understand that, both how to use that approximation and what it means. And to try to understand that, let's look at a toy example, a toy model. Think of this as a zero-dimensional path integral. So we've got an integral like this. So this, for those of you who have seen the path integral or functional integral, this is a zero-dimensional version of basically what we'll be doing. So in your quantum theory and QFT2 courses, we'll be looking at basically versions of this integral where instead of a single integral, we'll have infinitely many integrals. The idea is basically the same. And so the problem, a problem we'll often be interested in quantum theory or quantum field theory, is approximating integrals like this. Often when this parameter lambda, which will have the interpretation of a coupling constant, is small. So let's try to approximate this integral, assuming lambda is small. So in tutorial on Friday, I'll refreshed your memories of how to do Gaussian integrals. So the integral e to the minus x squared dx is an integral you all know how to do, as well as if we have any polynomial in front of that. This quartic term in the exponent, a priori we don't know how to do this. But if we Taylor expand e to the minus x to the 4, we can write it in a form that allows us to perform the integrals. So I've just expanded e to the minus x to the 4 in terms of its Taylor series. Now each term is an integral we know how to do. So let's go ahead and switch the sum and the integral. So that we can make further progress. And then what we get is a bunch of constants to the n factorial x to the 4n e to the minus x squared dx. Each of these integrals is something we can do. And we can use the techniques from tutorial on Friday. We can also note that this, if we do a change of variables, this actually looks like a gamma function. So if we take u equals x squared, then this integral will reduce to an integral of this form. I'm going to use that method today, but we could also use the methods from tutorial. So I'm going to take u equals x squared. Then we get e to the minus u, 0 to infinity, u to the 2n minus a half. And this is just a gamma integral. Gamma of 2n plus a half. So we've succeeded. I mean, this is basically, we're going to do fancy versions of this in quantum theory and quantum field theory too. But this is our, in a nutshell, our main technique for doing perturbation theory in those contexts. And it seems like we succeeded. So what's the point of the next 2 lectures? Well, let's think a little bit more carefully about what our result means. So we know that gamma of 2n plus a half for n large is approximately 2n factorial, which so for n large, we'll forget about the difference between a half and 1. So here we're multiplying 2n integers together. One set of those integers is n factorial. The other set is the product of 2n down to n plus 1, which is certainly greater than n factorial. Each of the integers is greater than each of the integers in that product. So this is bigger, certainly bigger than n factorial for n large enough. And so that means this is greater than the sum minus lambda to the n times n factorial. So the coefficients here are growing factorially, which means this sum certainly doesn't converge for any lambda. This is a divergent series. But as I mentioned before, this is our main technique for doing perturbation theory and quantum field theory. So it would be tragic to abandon this technique simply because our sums don't converge. So if we gave up every time we ran across infinity, we wouldn't get very far in QFT. So we're going to need to make sense of this series. It does have a meaning, and there is a sense in which this series does approximate the original integral we're interested in. It's simply not the first interpretation that came to our mind. This is not equal to this. It does contain information about this, the original series. And what this series is it's a first example of an asymptotic series. So this is an asymptotic series. Any questions so far? Okay, so let's define what's meant by an asymptotic series. I need a few definitions first. So our first definition is that a function f is much less than a function g as x approaches x naught if f of x divided by g of x, the limit as x goes to x naught is 0. Okay. So this is read as much less than. So one example is that x is much less than 1 over x as x goes to 0. So here's a question for you. True or false? If f of x is less than g of x, then f of x is much less g of x. Sorry, I want to do it the other way. If f of x is much less than g of x, then f is less than, let's say, as x goes to x naught. So I'm going to give you a minute to think about this, and if it's true, determine if it's true or false. If it's false, try to think of a counterexample. I'm going to give you a minute to...
Sorry, is the second inequality everywhere, or just as x goes to x naught as well?
Let's say for all x.
Sorry, can I have an unrelated question? Is this the same as the big O notation?
Yes, it's very closely related. You've made a decision, nod your head. Most of you? Okay, so how many think it's true? 1 for true, 2 for false. Okay, most of you agree. So can somebody? It's correct that it is false. Somebody give me an example.
X far less than 1 by x, that itself is an example. I mean, when you go to, for example, more than 1, then x is greater than 1 by x.
So x.
So x is greater than 1.
Yes, if
X
x
is-
is greater than 1,
If x is greater than 1.
then x is greater than 1 by x.
6. Okay, so in some restricted, if we restrict the allowed values of x, that this example works. I had in mind an example where this was true for all x, particularly including the limit point,
So you take -1 over x
minus 1 over x.
instead of 1 over x.
Sure. So that's an example. So yes, that doesn't change this relation. Another example is x squared is much less than -1. As x goes to 0. This is greater than 0, but much less than -1. Like that example. Your examples are good too.
Isn't that the same? That's the same example, just multiplied.
Multiply, yes. Yeah,
X.
yeah I think it, yeah, sure. Okay. Our second definition is f is asymptotic to g as x goes to x naught if f minus g is much less than g as x goes to x naught, or equivalently, the limit as x goes to x naught of f over g is 1. Okay, so some examples. Very simple example, cosine of x is asymptotic to -1. X goes to pi. So this is cosine of x is equal to pi, equal to -1 at pi, and approaches that smoothly. So this limit is 1. Let's do another couple examples. All right. True or false? If the limit f as x goes to x naught equals the limit g as x goes to x naught, then f and g are asymptotic. This is a true or false statement. And you only give it 2 at once. If limit as x goes to x naught of f equals, let's call it y. So here's two more statements. I'll give you a minute or two to see if they're true or false. If they're false, try to come up with a counterexample. I have not made any other specifications. How many of you have made a decision? Nod your heads. Need more time? Shake your head. Okay. I think I'll poll the class. So how many think the first one is true? 1 for true, 2 for false? Okay. And the second one? Okay. Need to come up with harder questions. Most of you got it. Can somebody give me a counterexample for the first one? Yes, Bachi.
E to the minus 1 over x and say 0.
Okay. Yes. Good, and that's it works for both, I guess. So the limit as x goes to 0 of this is 0, but nothing can be asymptotic to 0 because you put a 0 in the numerator or denominator here. It doesn't work. Okay. And so this leads us to the definition of an asymptotic series. So y has an asymptotic series. As x goes x naught, if y minus the partial sum up of the first n plus 1 terms is much less than x minus x naught to the n for all n.
That means convergence, or?
This means that y has an asymptotic series. So this is saying that if we take the partial sum, the difference between the true value of the function and the partial sum goes to 0 faster than x to the n as we get close to the limit point. It doesn't mean that the series converges.
Does it have to be for all n, or for all n above a certain threshold? Like n0.
It has to be for all n.
Why?
So each term in the series will tell you something about how the will give you more information about how the what happens as we get close to the true value of the function. So if we just required this for n sufficiently large, in particular, that wouldn't. Usually in physics, we can only calculate a few terms, maybe only 1 or 2 terms in the asymptotic series, and those terms will still give us information about what we're approximating. It wouldn't if we relax that restriction. Okay. So that's what an asymptotic series is. And a few comments. So convergent series become better approximations as we take more and more terms. You can always improve your accuracy if you take more terms with a convergent series. If you take enough terms, it eventually gets within any error tolerance of whatever you're trying to approximate. That's not necessarily true for an asymptotic series. What the definition of an asymptotic series says is that if we get close enough to x naught, then our approximation becomes good. It doesn't say anything, or gets better. It doesn't say anything about whether including more terms will help or hurt our approximation. So an asymptotic series is guaranteed to gets better as x goes to x naught with a fixed number of terms. Taking more terms can and often does make the approximation worth, particularly for asymptotic series that are not convergent. If you take enough terms, your approximation is certainly going to get worse. So it's possible for a series to be both convergent and asymptotic, convergent but not asymptotic, asymptotic but not convergent, or neither. So all those are possibilities. In general, different things. Although if we have a convergent series, common case is a convergent series with a finite radius of convergence, then it will be both. So that's a very common case. Okay. So suppose we have an asymptotic series or some quantity of interest. So if we add b times e to the minus c over lambda squared to f, then the asymptotic series will be exactly the same. Because c to the e to the minus c over lambda squared is much less than lambda to the n. Lambda goes to 0 for all n. So this term is invisible to the asymptotic series. So this is what's known as a non-perturbative function. Because in physics, we often construct asymptotic series using perturbation theory. But in general, we'll miss, if we're using perturbation theory, we'll miss things like e to the minus 1 over lambda squared. So perturbation theory is not the end of the story. And non-perturbative physics will be completely missed when we're doing perturbation theory. If we're using the if we use the saddle point approximation around the trivial saddle point, we'll completely miss some interesting things. And so in Q53, we'll discuss some of the non-perturbative physics, things like instantons that can have interesting effects. So an example of a non-perturbative effect you're probably familiar with is tunneling in quantum theory. So tunneling typically goes like e to the minus 1 over x or 1 over x squared in some perturbation parameter. So it's invisible in if you're doing it's invisible to perturbation theory. I'll just leave it at that. A final comment is that asymptotic relations are generally only valid in a wedge. In the complex plane. So far we've implicitly been working with real variables. We won't always want to do that. And if we have a complex variable and we're trying to construct an asymptotic relation, it's generally only works in some part of the complex plane. And to see that, well, we can look at this non-perturbative function. So it's completely invisible if we take lambda to 0 and lambda is real. Then this asymptotic relation, then e to the minus 1 over lambda squared is much less than lambda to the n. That won't be true if we take lambda to be imaginary. So then we'd flip the sign here, and this would blow up. And so this would change the asymptotics. Okay, so the most useful method for physics, in particular for applications to quantum theory and quantum field theory, of obtaining asymptotic series requires an integral form for whatever we're approximating. So that's naturally given to us in the path or functional integral quantization. So we're going to focus on obtaining asymptotic relations, asymptotic series, starting with something in an integral form. In our first example, how this works would be Stirling's approximation. This is a simple example of a real integral with a real expansion parameter that illustrates some of the ideas in the general case, and we'll add some more complications tomorrow. So we're trying to calculate in Stirling's approximation is the approximate value of n factorial, or gamma of n plus 1 for large real n. And so as we saw at the beginning of lecture, gamma of x plus 1 is given by this integral. And we're interested in approximating this integral for x large. The integrand looks something like this. So e to the minus t goes to 0 rather rapidly for large t. So over here, our function is going to 0. It also goes to 0 very rapidly for t small, because x is large. So it goes to 0 also very rapidly as t goes to 0. And so the integral is highly peaked and becomes more and more peaked around some value as x goes to infinity. And so the basic idea behind Stirling's approximation and the more general applications of the saddle point approximation we'll talk about next time are that we're going to basically approximate the integrand using as a Gaussian integral, which we know how to do. And that Gaussian integral will become more and more peaked, so our approximation will become better and better, in a sense, as our expansion parameter becomes bigger. So we want to make this look like a Gaussian integral. To do that, we can make a change of variables. T equals Wx. And what we get is minus x w, and we can put the this part in the exponent as well, log of w. And so the reason we made that change of variables is now our integral is in form like this, where our expansion parameter is multiplying a function in the exponent. So as the expansion parameter becomes bigger and bigger, this integral becomes more and more dominated by the values where f is near its minimum. And most of the integrals we'll be interested in, we can put in this form. If we're not given it immediately, we can massage it to make it look like that. So the idea is we're going to approximate this. Most of the contribution to this integral comes from when f is small, when x is large. So what we want to do is expand f. And around its minimum. So f prime is 1 minus 1 over w. So it has local min, or global min at w equals 1. So the integrand is maximized when w equals 1. So we can expand w around w equals 1. At w equals 1, log is 0, so we just get 1. And the second derivative will just give us 1 over w squared, so we get plus a half w minus 1 squared. And so that means that we can write gamma of x plus 1 as x plus 1 e to the minus x integral minus x over 2 w minus 1 squared so this is now a Gaussian integral. We forget about the higher order terms. Which we can evaluate. Well, it's almost a Gaussian integral. Our integration range is wrong. But for x large, this integrand is highly peaked around w equals 1. And so only a small region around w equals 1 will contribute meaningfully to the integral. And so if we extend the range of integration from 0 to minus infinity, we're not changing the value of the integral very much. The integrand is already tiny at 0, and it only gets smaller as we take w to be more and more negative. So we're not making much of an error if we just extend the range of integration and approximate this as a Gaussian integral from minus infinity to infinity, which, based on Friday's tutorial, we can evaluate. It just gives us root 2 pi over x. And so that's what we get here. And so this gives us an asymptotic relation for gamma of x plus 1 over root 2 pi the x plus a half e to the minus x. So that's asymptotic to 1. So that's the first term in our asymptotic series. If we kept more terms than dot, 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 we could get the next term. This is as x goes to infinity. And if we wanted to keep the more terms in the plus dot, 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 again, we don't know what to do if we keep them in the exponent. But like we did with the first example, where we had a quartic term in the exponent, we can Taylor expand e to these extra terms and write those as Gaussian integrals with a polynomial in front. So this is our first example of a asymptotic series that we constructed by approximating an integral with the sum of Gaussian integrals. And tomorrow we'll add some complications to this. So we're going to do tomorrow the saddle point approximation. Say a few words about this. So what we'll be interested in are integrals that in general given by some contour integral, some function times e to the z with some other function of w. This will be a contour. As with this as z goes to infinity. And what we'll show is that we can use basically the same idea as before. There'll be some additional complications, but the basic idea is the same as before. We massage our integral until we can write it as the sum of Gaussian integrals. And we can, we'll basically approximate this function as Gaussian integrals that if f has some local maxima, the integral will be concentrated around those local maxima. Those will be, there are saddle points here. Then we can deform our contour so that it passes through those saddle points so that our integral can be written as a sum of Gaussians. So some of the complications we'll need to take into account are if this is a complex integral and the phase changes, we can get destructive interference. So we'll need to be careful about that and see what which saddle points will contribute. So that's where we're going tomorrow. There'll also be some interesting things that happen if we take z to infinity in different directions in the complex plane. So as I was referring to before, asymptotic series are generally only valid in some finite wedge. So that's Stokes' phenomena we'll go into tomorrow as well. Are there any questions? Okay, I'll see you this afternoon.